Good day everybody, welcome to the second recording of Module 5, Chemical Changes in Fats and Oils. In this section we're going to focus on lipid oxidation. As I usually mention all the time, the work that is going to be covered in this video is a summary of work extracted from other sources, and those sources include textbooks. So part of your notes you will find references as to what textbooks to look at so that you can have in-depth understanding of the content. And secondly, as I already mentioned in the other video, is that you need to have a strong foundation in the knowledge of the triglyceride structure, the nomenclature, whereby you need to know your systematic and common naming of your fatty acids. You need to know about the chain length and the saturation and how it affects the functionality of a fatty acid. By understanding all that, you will be able to understand lipid oxidation and hydrolysis. Okay, so what is lipid oxidation? Lipid oxidation is defined as a spontaneous oxidation, or we can say reaction, of any substance, and in this case we're talking about the lipid coming in contact with molecular oxygen. So spontaneously those two react, and it's known as auto-oxidation because it's spontaneous, it just happens. Okay, so when this is happening on the lipid, on what exact site or part of the lipid is this taking place? Lipid oxidation takes place on the hydrocarbon chain of the fatty acid. Unlike hydrolysis, which takes place on the ester bond, lipid oxidation takes place on the hydrocarbon chain, and there it targets the hydrogen. So it targets the hydrogen. What usually happens is that your unsaturated fatty acids, those with a double bond, 2 or more, what happens is that they are more susceptible to oxidation. And the reason for that is that part of the initiation is required is to have the hydrogen obstructed. And it has been proven that a hydrogen that is obstructed from a polyunsaturated fatty acid requires low level of energy to obstruct compared to when you're obstructing a hydrogen from saturated fatty acids. So that does not mean that lipid oxidation would never take place. It's just that it will take longer because of the amount of activation energy required. So all type of fatty acids from unsaturated to saturated will undergo lipid oxidation, but it will be much easier with the unsaturated fatty acids. Okay, so as much as we had said that oxidation is spontaneous, whereby the lipid reacts with oxygen, there is part of lipid oxidation whereby it is catalyzed by an enzyme, and this enzyme is known as Lipoxygenase, which targets what we call the 1.4 pentadiene structure of a fatty acid. We'll talk about that later when we talk about those structures. So lipid oxidation, the mechanism goes via what we call a free radical mechanism, which contains a few steps. The major steps are 3, and then there's also sub-steps within the major steps, and this is known as the Farmer's hydrogen peroxide formation mechanism. So what you're seeing now in slide 28 is just the shorthand version of the actual reaction, but in the next slides coming, that's where we're going to focus on the actual fatty acid structure so that we can see what's happening. It's much easier there. So the steps are your initiation, propagation, and then termination. So let's go to it. Okay, so this slide looks very busy. However, I tried to number the steps so that you can follow. Okay, so here in this slide, we're going to make an example of oxidation of oleic acid. So as you can already see here, we have a triglyceride structure. When you have a triglyceride structure, you have a glycerol molecule esterified to 3 fatty acids. So the one fatty acid that we make an example of is oleic acid. But let's remember what I mentioned back there, that the fatty acid with the most unsaturation, which has got the most double bonds, will be the first to obstruct. But for the purpose of this example, I just used oleic acid, which is much easier compared to other polyunsaturated fatty acids. Okay, so in step number 1, the first step is you have a lipid, a triglyceride that is obviously a composition of a food product. It can be your sunflower oil. It can be a product made with sunflower oil, a high-fat product. Okay, so those triglycerides are there. They make up the lipid. They make up maybe 20% of the product. Okay, so in the initiation step, what happens in the initiation is that we have what we call hydrogen obstruction, like I had mentioned. Hydrogen obstruction is that of the hydrocarbon chain, as you can see as it is here. On the hydrocarbon backbone, what happens is that a hydrogen will have to be obstructed from this fatty acid. But I mean, there are so many hydrogens. Which one? How do we know which one will go first? As I had mentioned, that the easiest hydrogen to obstruct would be one that is adjacent the carbon that contains a double bonds. So it's usually the carbon that's adjacent. So as we already know, oleic acid has 18 carbons with one double bond, which is located at carbon number 9 from the carboxylic side. So what happens is that the adjacent hydrogen would be connected to carbon number 8 and carbon number 11. So when it comes to obstruction, obstruction is going to take place either at 8, and then at 11, either one of those. So I just chose carbon number 8. So what I want you to do, I want you to do a self-study with carbon number 11. So what happens is that the hydrogen is obstructed. But how is this hydrogen obstructed? Is that we talk about food production. In food production, we require high temperatures of processing, and we also do store food product in conditions that obviously will not deteriorate the shelf life. But it also happens that there's also the break of the cold chain and abuse there. So what happens due to that, when the product is abused, it might be stored in an area where there's light, exposed to light, and it can be stored in a warehouse or wherever, or at home in a kitchen windowsill where there's high temperatures because of the sun. And then also at the same time, it can contain metals. Some of these metals are obviously part of composition of the food product, especially with oils, because these metals can also be shaved during refining of oils using those equipment that they use in the oil refining industry. So as we already know that our metals, especially your iron and copper, they undergo oxidation reduction. So as a result, what would happen is that your metals or any of these initiators or catalysts, what they do is then they will obstruct a hydrogen, and when they obstruct a hydrogen, they are taking it out from the actual fatty acid, and then that hydrogen is like a lost hydrogen that's found in the system. It's like you extracting your tooth and then put it on the table. It's no longer on your mouth, but it's just there in the environment. Bad example, but yeah, that's how it works. So then when that happens, that is known as the alkyl radical, because a radical means something is unstable, and we already know that for carbon to be satisfied, it must have how many of the atoms on the outside valency. Still remember chemistry 1. So it's not satisfied because the hydrogen is removed. It's actually attached to 3, and then that's why it becomes a radical, because the hydrogen was produced or taken out, and that is known as a hydrogen radical, and then this is then known as an alkyl radical. So after the hydrogen obstruction, then the fat is in what we call a radical form. It's an alkyl radical, and when something is in a radical form, it becomes highly reactive, and becoming highly reactive, it means it will react with anything that wants to react with it. And then that is when we come to this phenomenon of spontaneous oxidation, because now the oxygen then reacts with the alkyl radical to form what we call the peroxyl radical. Like we mentioned, it's highly reactive. It will react with oxygen. Oxygen will never oxidize a fatty acid that's not in radical form. It will not react with a fatty acid that the hydrogen is not obstructed. It can never. So this oxygen can never come and oxidize here, but it can only start oxidizing or reacting once the alkyl radical is formed. After, when the oxygen inserts there, now you have what we call the peroxyl radical, and that is step number 2. We call it the self-propagation step, whereby oxygen is added. Remember, the oxygen is in the surrounding. Maybe the food product is stored in an area where it's open, or maybe the oxygen transmission rate of the packaging is quite high, so oxygen can go in and out freely. You know, the environment affects that. So with that oxygen reacting in there, you form what we call a peroxyl radical. But this fatty acid is still in a radical form, so it's still highly reactive. And when it's highly reactive, it has to react with something else. It can't react with oxygen anymore. But what does it do? So after step number 3, then step number 4 is, because this peroxyl radical wants to be satisfied, it goes back again now to the fatty acid. Remember, it took from one fatty acid within the triglyceride, then it goes to another fatty acid there, and then it obstructs a hydrogen. By obstructing a hydrogen, this hydrogen then reacts with the peroxyl radical to form what we call a lipid hydroperoxide. However, as much as this lipid hydroperoxide is now satisfied, it's no longer in a radical form, what happens back there in the fatty acid? This fatty acid is now in a radical form. So if this fatty acid is in a radical form, what's going to happen? Oxygen will come in there and do the same thing, and then obstruct a hydrogen from another one. So it becomes a chain reaction, and therefore it means hydrogen will be obstructed from each and every fatty acid. So the whole fat or the whole triglycerides within the product will then be in a radical form. So the lipid hydroperoxide is formed. Lipid hydroperoxides are very stable. When they are stable, what happens is that they are quite stable, but then they can also break down, and I'll talk about why they break down. So when lipid hydroperoxides are formed, this whole step here, or whole process, this product is formed, and these are also all known as primary lipid oxidation products. So this is the stages. So we can say stage 1, whereby you form primary lipid oxidation products, and those are your lipid hydroperoxides. One thing you need to know about lipid hydroperoxides is that they are quite stable, yes, when they are formed, and then they accumulate over time. So remember, each and every fat is being converted. Each and every fat is being converted, and then they accumulate. And after accumulating, usually after when there's a lot, then it breaks down. So lipid hydroperoxides, before they break down, once they are still stable, they are colorless, they are odorless, they are tasteless. So it means that food product, you can't smell any rancidity, nothing at all, because of the primary lipid oxidation products. But that does not mean that oxidation has not started. It's halfway there. It has formed products. It's just that you cannot perceive them as yet. It's more like somebody who's pregnant. You usually see that a person is pregnant once the stomach bulges, and I think that's 3 months to 4 months. But a person can also be pregnant for 2 days and there's nothing to see yet. Okay? Stupid example, but I hope it works. So those are termed primary lipid oxidation products. They have formed already. So looking at here, you can see that the lipid peroxide formed at carbon number 8. So we also give this peroxyl radical's name, lipid hydroperoxide's name. So this one is 8-hydroperoxy, because it's a hydro, it's a peroxide. 9-inoic acid. So 9, that's where the double bond, that's where the in is. Oic means it's a fatty acid. So inoic acid, in for your double bond. So primary lipid oxidation products are formed, and then they are quite stable. Okay, before going on to the breaking down of the lipid hydroperoxides, I wanted to also talk about lipoxygenase. We spoke about lipoxygenase being the enzyme that can also catalyze oxidation. So instead of having your initiators as light metals and obstructing of hydrogen needing high activation energy, here the enzyme will do everything. So it lowers the activation energy required for this chemical reaction to take place. So now, as we already mentioned, lipoxygenase is specific to what we call a 1.4 pentadiene. So it only catalyzes a reaction whereby there are double bonds. There must be 2 double bonds, and there must be in the specific sequence. So 1.4 pentadiene is when there's this double bond in there. Okay, so as you can see with the double bond, it's at carbon 1 of the pentadiene, 1 and 4. So that is why it's called 1.4 pentadiene. If this bond was here, then that obviously wouldn't be a 1.4 pentadiene. It will be a 1.5 hexadiene, so which obviously is not a substrate. So what lipoxygenase does is it catalyzes your 4 steps. Okay, it abstracts the hydrogen, it rearranges the radicals, it inserts oxygen, and then it forms lipid hydroperoxide. So we can just say, in actual sense, the complete reaction is that lipid hydroperoxides are formed by lipoxygenase. Once at all, we already know that enzymes obviously catalyze the reaction, and then boom, you have your lipid hydroperoxide. It will still be the same as the ones that are produced via your normal light, heat, and whatsoever type of catalysts. So this lipid hydroperoxides that are formed also, they are also stable. But usually what happens is that lipid hydroperoxides, under the propagation step, they also decompose. The reason why they decompose, as much as I had mentioned that they are stable, they decompose because the very same conditions that allowed the product to be oxidized in the first place, they still prevail. That product is still left in that warehouse at high temperatures where there are metals and where obviously there's light coming through and so on. So those conditions then accelerate the decomposition of your hydroperoxides. So in step number 5, here's your formed lipid hydroperoxide. And then what happens is that decomposition, once it starts breaking down, when it just breaks down and it's no longer a lipid hydroperoxide, those are termed secondary lipid oxidation products. So what happens is that with your lipid hydroperoxides, they are broken into what we call a hydroxyl radical, and then what's left there, it's a single bonded oxygen, and that's known as the alkoxy radicals. So this OH radical also gets into the system like that other hydrogen that was also lost in the system. So there are so many other radicals that are formed that are just lost in the system. That's still within the food product. And then after that, after the alkoxy radical has been formed, what happens is that the next step, number 7, is what we call homolytic scission. Homolytic scission, that's whereby you actually have the cutting of the fatty acid or hydrocarbon chain in half. Okay, when we do lipid oxidation, when we continue with lipid oxidation in higher levels of study, we talk about different types of homolytic scissions, whereby where the alkoxy radicals is formed and then carbon, there's breaking on both sides. But for the level of food chemistry that we're doing here, we're just going to focus on the one homolytic scission, which is on the left hand side. So on the left hand side of the carbon that contains the alkoxy radical, there's what we call the homolytic scission. So there's breaking, and that breaking is also accelerated by the conditions. So then you actually have 2 parts. The first part is the part of the fatty acid that is still attached to the glycerol, and then you also have the other part of the fatty acid on the side. So if you can see the other part of the fatty acid now, you actually have a radical there, which obviously now forms part of the radical species within the what? The actual system. And then at number 9, that's when you find that you have the carbon with an alkoxyl radical with a hydrogen. And then what happens is that because of that bond there, there's bond migration that takes place, and that now becomes an aldehyde. So you can see the single bonded oxygen, which was a radical, becomes fulfilled by bond migration, where you see an aldehyde formation. And then when this aldehyde forms, this aldehyde are termed secondary lipid oxidation products. And as I already mentioned, your primary lipid oxidation products don't smell, don't taste, don't have any color. However, once they break down and form these secondary lipid oxidation products, that's where you perceive rancidity. So that's when you can smell the aldehydes. When you smell that old fish oil smell or whatever, it's due to the secondary lipid oxidation products. So your aldehyde formation, there are other steps that take place or in terms of how the alkoxy radical breaks down, but it's not for the study. So the aldehyde formation because of the aldehyde functional group. So then going back to the systematic and common naming in chemistry using the IUPAC, we have to give this chemical that's being formed a name, because we then obviously count the number of carbons, look at the functional groups and everything using your organic chemistry. Remember, we never learn to forget. So by looking at this aldehyde has a double bond, so it's an ene. So what we do is we count the number of carbons. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So 11. So if we go back to basic organic chemistry, we talk about methane, ethane, propane, butane, heptane, hexane, octane, nonane, decanal, and then you also have 11 is undecanal or undecane, okay? But if it's an alkane, but now we realize that this is an alkene because it has a double bond, and it's just not any special alkene, it's an alkene with an aldehyde group. That is why it is then termed 2, because the double bond is on position 2, undec because it's 11, uno plus dec, 1 plus 10 is 11, undecinal, quinal because of the ene, and nal because of the aldehyde, or you can call it undeca 2 enal. So it means that you need to give each and every of those aldehydes that are formed names, and that obviously stems from your history with organic chemistry. Okay, so the next slide is just showing you, remember I told you that with this secondary lipid oxidation product, the way those hydroperoxides and alkoxyl radical break, they have so many pathways, but we just followed the aldehyde pathway, never mind all the other pathways. So going back here, we had mentioned that there is this radical that was formed. There's the hydroxyl radical that is also on the system, and then going back in there, there's this hydrogen radical that is also floating around. There's another radical there. So the last step, which I obviously did not include in terms of the schematic diagram, is known as the termination. In the termination step, that's where you have your free radical species reacting together. When they fuse together, they become non-radical species, and in that way they terminate the reaction. However, termination is a little bit too late because aldehydes have been formed. They bring about rancidity. So it's more like you going, there's a fire and the whole house burns, then you manage to contain the fire, but everything else has burnt. So the damage has been done. But termination takes place when all the aldehydes and all, not the aldehydes, all the still things that are still in radical form fuse together. So these other slides are just the explanation of what I've been talking about. Go read about it. And then the aldehyde, alkoxy radical forming aldehyde generation is what we focused on, but other things that might be formed via other pathways will be formation of ketones, reduction to alcohol. And then later onwards, because there will be so many triglycerides within that product, and there are so many aldehydes and ketones and everything formed. So what those things do is that they polymerize, they react. Those monomers form polymers. And then as a result, that is why sometimes you find that cooking oil, or aka fish oil, would be a bit sticky and gummy and viscous. That will be due to polymerization, and that is usually also accelerated by high temperatures, especially high temperatures of frying, like reusing the oil all the time. So it becomes that. As much as it's a bad thing in food, people in the paint industry rely on that to form paint. Okay, so polymerization will also take place. So later on, we'll also talk about the kinetics. What happens? How do we go about monitoring lipid oxidation? Thank you.